All right, chapter 4. We're going to be covering the different types of chemical bonds. So you have ionic bonds and covalent bonds, the main two chemical bonds in general chemistry. There are other bonds that are such as metallic bonds, which by the name you can tell it's all by metals, all through metals. But we're not going to cover that in this class. We'll cover the main two. So this is just saying that, carbon. Yeah, so carbon exists as different forms. You have carbon is in your pencil, you have graphite, and you have graphene, which is another form of carbon, which is very strong. Then you have the hardest material, which is diamond, which is also just plain carbon. So that's all based on the exposure to carbon in pressure, different pressures. And they actually make the carbon atoms make a different three-dimensional structure when they are in these different materials. So this is an example. These carbons take kind of like a lattice, and it's just like covalently bonded carbon together. So we'll be talking about this, but before that, we'll talk about ionic bonds. So ionic bonds are prevalent in salt. So when I say salt, I don't just mean NaCl that's pictured on the screen. I mean different types of salts. Like road salt is not NaCl. That sometimes is a KCl, meaning potassium chloride. And also there's other types of salts. Magnesium sulfate is a salt. Anything that has a metal and a non-metal is really in an ionic bond is considered a salt. So yeah, so there's different types of salts. Now, the nature of the ionic bond is you have charges that are involved. So you have a positive and negative charge that's involved in the attraction of the two, what we call ions. So it's called an ionic bond, and ions partake in the ionic bond. So that's what these are called, ions, I-O-N-S. And there's positive ions, which is in this case sodium, Na plus ions, and then there's Cl minus ions. So that's another ion, and they come together, they have opposite charges, and they create the ionic bond. So here's basically how it looks like in 3 dimensions. If you go in the atomic view, very, very close up in NaCl, you see this Na happens to be smaller. Actually, no, this is false. Cl happens to be a lot smaller than Na. So I don't know why this representation is wrong. So but the premise is right, where you have sodium plus and Cl minus, and they're bonded together. So so yeah. So here's going into depth of what exactly happens. Now this is something that a lot of teachers, at least in high school when I learned it, was taught wrong, where how is the ionic bond actually produced? So what happens first is based on the chemical nature of each of the atoms involved, or each of the elements involved. Let's say we have sodium and chlorine. Chlorine is a nonmetal. Yeah, we learned about the different types, the organization of the periodic table. It's in group 7A. Therefore, it's a halogen, right? And these halogens are very susceptible to gaining electrons. They have a very high electron affinity, meaning if they come into contact with something that has electrons to give, they are going to take that electron very quickly. And then you have sodium on the other hand, which kind of helps this process and facilitates it because it has a very low electron affinity, meaning it wants to get rid of an electron. And it only has one valence electron, and it wants to get rid of this electron. And we'll talk about why in the next slide. And for the same reason why chlorine wants to gain that electron. So when they come into close contact, kind of think of it as, I don't know, something where, I can't think of examples, it's too early, but let's say another one man's trash is another man's treasure, right? So chlorine wants to gain electrons really bad. Sodium doesn't even want his electron. So sodium's like, I'll give it away for free, I don't care. Oh, chlorine, you want it, it'll make you happy? Sure, take it. So it's a very seamless process. There's not really much energy involved in that process of that transfer of the electron. Now, what that transfer of the electron does is once it transfers, and you picture that originally chlorine, you see, has 17 protons. Every chlorine has 17 protons based on the periodic table, but it also has 17 electrons initially because it's neutral. When chlorine gains that electron from the sodium, it now has 18 electrons. Now that differential between 17 protons and 18 electrons gives it an ionic charge. The ionic charge is -1 because the electrons outweigh the protons by 1. So it has that -1 charge. And on the other hand, The sodium, which originally is neutral, 11 protons, 11 neutrons, 11 protons, 11 electrons, now loses an electron, meaning it loses a negative, which means it becomes positive. So it becomes positively charged. So this is how the charge is created. Once the charge is created, that induces the bond. So it induces them coming closer together, kind of like a magnet, that a positive or north and south end, positive, negative end, they come close together. Now, it's not, so some people teach it as the sodium's positive, chlorine's negative, and they come together. No, they're both neutral. So the transfer of the electron induces the charge, which brings them together. So think about it like that. Once the electron's transferred, then they have the necessary charge to come together and attract one another. And this makes both the metal and the nonmetal have charge. So here's basically how it happens. So they come close together by random motion. The sodium gives the electron to the chlorine. Once that happens, that induces the charge, which then brings them closer together. And that's one type of an electrostatic interaction, electrostatic attraction. And really, all these bonds are electrostatic, so it's kind of redundant, but this is an ionic bond. Any questions on that, on how that forms?
So they're basically kind of like attracted to each other, like as they give.
Yes, as the electron transfers, then they become attracted to one another.
Okay, got it.
Okay, cool. Okay, so here's some examples of some salts. Now there's different types of salt. There's calcium, that's a metal. There's iron. Iron sulfate is a salt. Really anything that partakes in this ionic bond is a salt. And a lot of them are harmful. A lot of them are not harmful. So like sodium chloride is not harmful for you. You can eat it. But other ones like iron sulfate's not harmful. I mean, it's in the supplement. But there's other ones like potassium chloride is an irritant, for example. So they have different properties. Okay, so something that the ionic bonds follow, a rule that they follow, and not only the ionic bonds, but all of these bonds that we're going to learn about today, they follow this code of 8, known as the octet rule. So octet, like octopus, right? 8. So what this means is that the electrons that are partaking in these bonds are the valence electrons. And we've heard of that term before. And the valence electrons mean the outermost electrons that are the most reactive, and they partake in these bonds. And it makes sense physically, right? Because if you have two atoms that are coming in physical contact with each other, the first electrons that are going to make contact or interact with each other are the ones of the outermost shell. So if you throw a basketball at a wall, the inside of the basketball is not going to hit the wall. The outside is going to hit it first. So same concept. And that's what makes these electrons the most reactive. They're going to have the higher likelihood of reacting with another atom nearby. So they like to have, in this valence shell, so the electrons as depicted here, you see how the electrons are in different shells? The outer shell is the valence shell, meaning they're the most reactive, right? So they like to have really both types of atoms, the positive ones and the negative ones, like to have 8 electrons in that shell, in the outermost shell. So let's stick on this slide for another second just to show you how that happens. Now, chlorine is in 7A, right? 7 valence electrons, group 7A. It needs one more to get to 8, that golden octet rule. So it makes sense how when sodium gives it the electron, it's happy. And it makes sense why it wants an electron so bad, because it has 7, it just needs one more to get to 8. So that makes sense. Then you have sodium. Sodium has 1 valence electron. It's in group 1A on the periodic table. So it needs 7 more to get to 8 valence electrons, right? So you may think, okay, why doesn't sodium just go to other atoms and get 7 electrons? And the answer is that takes a lot of work. That takes a tremendous amount of energy to do that. So atoms are smart, or they're lazy, which makes them more efficient, honestly. So what that means is, instead of gaining 7 electrons, if they lose 1, like they tend to do, look at their new inner shell on the right side here. The new outer shell. Since the old outer shell is gone, there's no more electrons that occupy it. The new outer shell has 8 electrons. It's completely filled up already. So only removing 1 electron from sodium gives it the octet rule from the inner shell. And that inner shell now becomes the outer shell. And then chlorine, and just like the rest of the nonmetals, they like to complete the shell that they already have occupied by some of the electrons. And in chlorine's case, it has 7. Oxygen's case, it only has 6. Nitrogen and phosphorus's case, it has 5. Carbon's case, it has 4. So that's how that works, where the metals like to lose the electron in order to have 8 valence electrons in their old inner shell, which then, once they lose the electrons, becomes their outer shell. And then chlorine, like the nonmetals, they have a closer to 8 than to 0. So they like to gain the number of electrons they need to get to 8. That's the most energetically favorable thing to do. It requires less work. That's why they do it. So that's why the world works, because these chemical and biological process, this is not biological, but I'm just saying in general, the biological processes tend to take the easiest route for energy efficiency. So this is just a common trend throughout science. Any questions on how that works?
Well, I have a question, but
Yeah.
it's about which has more affinity for what?
So chlorine has more affinity for electrons.
So the chlorine is the nonmetal.
Correct.
Okay.
Okay, cool. So the nonmetals have the electron affinity. They have higher electron affinity than the metals. They want to gain the electrons from the metals. So, yeah, good question. Okay, so like I said, 8's the goal. And we know how that happens, because either by gaining or losing electrons. And also in covalent bonds, which we're going to talk about in a second, by sharing electrons, you could also get to 8. All right, so here's the periodic table. Just to refresh everybody, sodium's over here, 1A, left side. And they all have 1 valence electron. 2A has 2 valence electrons. In the middle, they have maybe 1, maybe 2, maybe 3, maybe 4. And then on the right side, you have the nonmetals, where they have a high number, close to 8 valence electrons. You have the halogens, which have 7. So here's chlorine right there. Once it gains 1 more, it gets to the electron configuration of argon, which is a noble gas, which is happy. So furthermore, that's why these atoms like to gain or lose electrons, meaning lose electrons by the metals, gain electrons by the nonmetals, is because they want to achieve a noble gas electron configuration. So the noble gases we talked about in previous classes, that they're happy, they're stable, they don't want to react with anything, and they're very low energy, so they're content. So if the other atoms can try to be like them, be like the noble gases, they will also be happy. And chlorine tends to gain 1 electron to be happy. Sulfur tends to gain 2, phosphorus 3, so forth. And then the metals like to lose. So the way to think about it when you're doing it on an exam, or thinking about this when you're doing homework, is if I ask you a question, how many electrons does nitrogen need to, or what would nitrogen's charge be? Now I'm going to show you a chart later, a modified periodic table that shows you the charges, and it's just easier to memorize them. But conceptually, if you want to see what the charge is of nitrogen, you're like, all right, it's a nonmetal. It's going to lose electrons, gain electrons. Now, how many? All right, we know it needs to get to a noble gas. So if it gains 1, it's at oxygen. If it gains 2, it's at fluorine. If it gains 3, it's at neon. So that means nitrogen must gain 3. And that's exactly right. So once it gains 3, its charge goes from 0 to -1 to -2 to -3, because it's gaining negative charges, because the electrons are negative. So does that make sense? And you can do that with every element in the periodic table almost. So like sulfur, It's 1 away. So you get to the nearest noble gas. 1, 2. All right. It takes 2 jumps. That means it gains 2 electrons. And once it does, it has a -2 charge. So any questions on that? It's an important concept. So that's why I'm really drilling it in there. If you understand it already, that's fine. I'm just repeating myself in different ways. So then let's look at the metals. Let's look at calcium, right? If you want to go to calcium, or let's look at magnesium. That's easier. So the nearest noble gas for magnesium, right? The nearest place it wants to go. If you gain electrons from magnesium, you have to do this. It has 2 already. Aluminum will be 3, silicon will be 4, and it goes 5, 6, 7, 8. That's too many. That's too many jumps. You want to minimize the jumps. So if magnesium goes backwards, instead of gaining electrons, losing. When it loses 1, it gets to sodium. When it loses another 1, it goes all the way back to neon. So when magnesium loses those 2 electrons, it becomes a noble gas configuration, meaning it's happy. So that's why, and that's energetically more favorable than gaining 6 electrons, is losing 2. So that's why they have a low electron affinity. Okay, moving forward. All right, so basically what I've just said already, just summarized into nice, complete sentences. And the sentences in bold are really good to know. So metals lose valence electrons to nonmetals, becoming positively charged cations. So that's a new term here. So the positive ions, they have their own name called cations. So the way I like to think about it, because I have a cat, is cats are good, so positive, right? So metals lose valence electrons to nonmetals, becoming positively charged cations. Then conversely, you have nonmetals, and we know they like to gain valence electrons to become negatively charged anions. So that's a new term here. These nonmetals, when they become ions, are called anions. So an meaning like anti or against, so minus charge. So those are the 2 terms for everything we just talked about. That's what they're called. So you have the metals are cations, the nonmetals are negative anions. All right. So here's an example of some ions, and you can kind of tell by looking at the periodic table what the charges will be, just like we saw before for sodium and for calcium as our example. But it's based on their group. So if you look at, let's say 7A, fluorine, chlorine, bromine, iodine, they're all -1. And that's because they only need 1 more valence electron to get to that noble gas configuration when you make that jump in the periodic table. So they want to gain 1 electron. Elements in 6A, oxygen and sulfur, they like to form -2. 5A likes to form -3. And then in the middle of the table, honestly, it gets weird. So we're not going to focus on that because it changes a lot. But for 1A, they're +1. For 2A, they're +2. For 3A, aluminum and gallium in 3A are the only ones that are +3, but gallium's not written here. And then you have some of them that are in the not noble gases. Some of them that are in the transition metals that are written on the bottom. You have copper, could either be +1 or +2. Silver is only +1. Zinc is only +2. Iron could either be 2 or 3. So you don't need to memorize this, but you're going to have to know the charges by looking at the periodic table. And we kind of already talked on how to do that, but I'll show you a comprehensive chart in a couple of slides, I think. Where is it? I'll show you right now. There it is. So there's a chart that would be good to memorize, honestly. Not really too much the iron and the copper, but more 1A, 2A, 3A, 5A, 6A, 7A. And it kind of makes sense based on the trends we already talked about, where the 7A, right, they have 7 valence. They need 1 more. Once they gain that 1, they become -1. 6A, they have 6 valence. They need to gain 2 to get to 8. Therefore, -2. 5A, they have 5 valence electrons. They gain 1, 2, 3 in order to get to noble gas. Therefore, the charge is -3. Aluminum in 3A is +3. So that means it loses 1, 2, going all the way back to neon, 3, in order to become a noble gas configuration. So that's why it's plus 3. Magnesium is plus 2 because 1, 2, like we talked about before. And sodium is plus 1 because it only needs to lose that 1. So does that concept make sense? And do you think with a little bit of practice, you guys would be able to figure out the charges of different ions? Because it is important for naming. Any questions on it? So, okay, so make sure you study that a bit. All right. So now we're going to talk about naming. The best way I like to teach naming is by example. If I already mentioned sodium chloride, right? So why is it called sodium chloride? If you look at the, let me get my pen out. 1 second. So let's look at sodium chloride. All right, so sodium chloride. Okay, so why is it called sodium chloride? And we know it's NaCl. Reason why is, let's look. Sodium, okay? If we look at the periodic table, that's the same thing. Na is sodium, and that's good. And that's it. So you just write the name of the metal in these ionic bonds. So you're writing the name of the metal. Na is sodium, you write the name. All right, sodium. Now Cl. Cl, if you look at the periodic table, is not chloride, it's chlorine, right? Like chlorine in the pool. So why do you write chloride? And really the answer is because that's what they said to do. And there really is no answer for that, is because that's the rule. So the chlorine should be sodium chlorine, right? That's not how to spell chlorine. Chlorine. But what you do is you get rid of the INE and you put an IDE. So you're getting rid of the last syllable and adding the IDE ending. And this works for a lot of them. So you, well, all of them almost. So you have chloride, sulfur becomes sulfide. Let's look at some elements real quick. Fluorine becomes fluoride. Bromine becomes bromide. Oxygen becomes oxide. Phosphorus is a tough one. It becomes phosphide, not phosphoride. Nitrogen becomes nitride. Carbon becomes carbide. So those are the major examples there. So that's how you're going to name ionic bonds. There are some more rules we're going to learn, but that's a simple way to do it. So in given a bond, let's say like MgS, something like that. Mg is magnesium, so it'd be magnesium. S is sulfur, but the second element, or the anion, it's always written cation, anion. So positive, negative. So it's going to be positive 2, minus 2. So sulfur becomes sulfide. So this becomes magnesium. And don't worry, we're going to do examples. Sulfide, like that. So yeah. Okay. So let's talk about the anion. So basically what I just talked about is that the anion, it has the name of the root name of the element plus the IDE ending. That's important. So, and keep in mind, this is only for ionic bonds. We didn't touch covalent bonds yet. That's the other type of bond, but they're easier to name. So that's that. And then for oxygen, you'd have a -2. It's an oxide ion. For chlorine, it would be -1. Doesn't matter. It's still chloride. So that's that. So here's some examples. NaCl, we know, is sodium chloride. MgO is magnesium oxide. We'll do some examples. We'll do some more. Let me think. We'll do KCl. We'll do. Here's one. We'll do a bunch. Let's think of some random ones. We'll do those three. All right. So start with KCl. Anybody want to give me the answer? What would KCl be?
Potassium chloride.
Perfect. Potassium chloride. Awesome. Good, because you're doing K is potassium, you just write the name of the metal. Cl is chlorine, so you change the ending to IDE, chloride. All right, now this is a tricky question. I know what someone's going to say, but I won't say it. Anyway, what is this? CaCl2.
Calcium dichloride.
I knew you were going to say that. So actually, that's wrong. So that's why I put that in there, because none of them had the numbers yet. So it's important to know this is actually calcium chloride. No dichloride. The reason is because, first of all, I didn't talk anything about prefixes yet. I didn't say anything about di, mono, di, tri, anything. You guys assume that because we hear this stuff in everyday terminology. What do we breathe out? Carbon dioxide, right? What will kill us if we breathe it in? Carbon monoxide. So we hear these things all the time. Those compounds are actually covalent. They're not ionic. So the thing about ionic bonds is they are very math-based. So if you write calcium chloride, there is only one calcium chloride, and that's CaCl2. The reader would know that if they know basic chemistry, like you do. And if you want to go further, the math reason is because if you look at the charges, it's the CaCl2 is the only way that calcium chloride could become a thing, right? So calcium, let's go back to the periodic table. So calcium, what's the charge? +2, right? It's in 2A. Chlorine, what's the charge? -1. It's over here. So if calcium is 2 plus, chlorine is 1 minus, -1, then the only way for these to balance out, equal and opposite, and become a bond is if you have 1 calcium and 2 chlorides. So that's the only, this is only the only possible way calcium and chloride can make an ionic bond if there's 2 chlorines. Therefore, the only name is calcium chloride. And if you write this name, it tells the reader, all right, it has to be this based on math. This is where a little bit of math comes into play. And once you go from the name to the formula, that's going to be important to know this, the math, that the positives cancel out with the negatives. They have to in ionic bonds. So any questions on that concept? We'll do more. Okay. What about the next one? So let's see. Close, sodium. So not nitroide. So for some of these elements, it's weird because you're getting rid of a little bit more than the last syllable, but it would be sodium nitride. And oh, why are you getting rid of more than one syllable? Honestly, the reason why is because it sounds better. So nitroide doesn't sound as flowy as nitride. Same with oxygen. Technically, it should be oxide, but that sounds stupid. So they make it oxide. And this is people that made these rules, right? These aren't rules of nature. This is just how we name the compound so everybody knows what we're talking about. And we want it to sound cooler. So, or sound easier to say. So sodium nitride, as an example, would be this. And again, it doesn't matter the number on the bottom, because the only way for sodium nitride to become a thing is we know that nitrogen is -3, sodium is +1. So you need 3 sodiums to cancel out with 1 nitrogen. So that's the only possibility. Let's do one more. We'll do SR3P2. Okay, so where's SR? So SR is right here. That's strontium. The charge of strontium is +2. And P is over here, which is phosphorus. The charge of phosphorus is -3 because it's in 5A. So if you go here, what would the name of this be? Anybody want to? Oh, wait, what did I do? That's not what I wrote. Here we go. That's what I wrote. So what would it be? I'll give you a hint. Strontium comes first. Strontium. Any guesses? Good. Spelling not exactly right, but strontium phosphide. So perfect. Good job. So it'd be phosphide. Oh, the S is covered. So yeah, sodium phosphide. Oh, sorry, it's not sodium. Yeah, strontium. Strontium phosphide. That's what would be it. And this is the only way. SR3P2. That's the only way for strontium phosphide to be a thing, because phosphorus is -3. Sodium is +2. Not sodium. I keep saying sodium. Strontium is +2. So the only way for these to make a combination for the positives and minus to cancel out is if phosphorus has 2 of them and if strontium has 3 of them. Strontium having 3 will make the charge +6. Phosphorus having 2 of them will make the charge -6. So if you have ions with a +2 and a -3 or +3 and -2, the best way to figure out what they become is you just switch the numbers. Or in other words, what we're doing is finding the least common multiple. So you know that the least common multiple between 2 and 3 is 6. So that's why the positives have to be +6. The minuses have to be -6. Okay, any questions on that? Okay. Moving forward. So the ones we've done so far, and let's revert back to the periodic table. The ones we've done were we only used 1A, 2A, maybe aluminum, and then everything else over here, right? We didn't touch anything in the middle yet. All of these transition metals. The reason why is because there are different rules, little modification, little tweaking of these rules when we're describing the metals that are in the middle, the transition metals. And it's because we don't know the charge of them per se until we know the formula. So for group 1A and 2A and aluminum and all the ones on the right and the nonmetals, we know these charges because they have a fixed number of valence electrons. This is +1, this is +2, this one's +3, this one is -1, -2, -3, and sometimes -4 for that. But carbide doesn't come around that often, mostly these 3. So we know these charges. These are the ones you have to know based on the secondary periodic table, based on this periodic, no, not that one, based on this one that I showed before. But you notice how everything else in white has, and even iron and copper have charges that are variant. They can vary. So how do we know what the charge is? And the answer is by putting Roman numerals next to the ions. So once we involve these transition metals into our ionic naming scheme, we're going to have to use another helper to the reader, meaning something to aid them in determining what the charge is. And that thing is the Roman numeral. So here's some examples. You have Fe2+. Since there are 2 forms of iron, like we saw here, there's Fe2+ and Fe3+. For copper, there's Cu+ and Cu2 plus, we can say that, all right, Fe2 plus is iron 2. Fe3 plus is iron 3. Copper 2 plus is copper 2. Copper 1 plus is copper 1. So we're making these little modifications to the ion. If it is not apparent based on just looking at the periodic table what the charge is. So for something like calcium, you wouldn't put calcium 2. You would just write calcium, because we know that calcium is always plus 2. This only applies to the ones that are in the middle that we don't know the charge of. So let's do some examples. All right. I'll write some examples. We'll do FeCl3, FeCl2, Cr2O, CuO. We'll do something crazy like Mn3N2. There we go. We'll do these 5 as examples. All right. So Fe3 or FeCl3. Anybody have any guesses for this one or answers? I'll give you a second. No? Okay, it's 8:40 in the morning, so I understand. On a Monday, so I understand. Let's do this together then. So what do we know whenever you're determining, so it's a general rule. Whenever we're naming bonds, covalent, ionic, whatever, transition metal, non-transition metal, whatever, we first need to determine what type of bond it is. And since we've only talked about ionic, it's ionic. Furthermore, we need to figure out which of the atoms we know the charge of from just looking at the table. So for chlorine, we know the charge of chlorine. It's -1. Since we talked about it for the last 20 minutes, see chlorine's right here. So it's -1, 7A. So if that's the case, then what must the charge of iron be? Each chlorine is -1.
Plus
There's
3.
3 of them. So
Plus 3.
Sorry, what was that?
Plus 3.
+3, perfect. Thank you. So iron must be +3. And this means the name of it is then what?
Iron 3.
Perfect.
Iron 3 chloride.
Good. Iron 3 chloride. Awesome. You guys are getting the hang of it. Iron 3 chloride. Nice. Good. All right. Now, if that's the case, what would this one be? The second one.
Iron 2 chloride.
Perfect. You guys are experts. Iron 2 chloride. And that's because same thing as chlorine. It's always -1. In this case, there's 2 of them. 2 times -1 is -2. Therefore, this iron has to be +2. Okay. Now let's do a little bit more complicated. This one, Cr2O. Now, Cr is chromium. Let's tell you that. Any guesses? Oh, sorry. Any guesses?
Chromium 2 oxygen?
Close. So I like the thought. She said chromium 2 oxide. Now, it's not chromium 2 oxide. Does anybody have any other?
Would it just be chromium oxide?
It wouldn't just be chromium, because let's look where chromium is.
It's in the middle.
Yeah, chromium's right here. So it's in the middle. So it doesn't follow well, we have to use our transition metal rules, meaning our Roman numerals. So it wasn't chromium oxide, and it wasn't chromium 2 oxide.
Chromium 1 oxide.
Perfect. Chromium 1 oxide. And do you want to explain why?
oxygen has a -2 charge, I think.
Perfect.
And so and chromium, I'm assuming, has 1.
Yes, in this case, that's important to mention. In this case, it has 1 because of the formula.
What do you mean by because of the formula? How do you figure it out?
Good question. So in this case, for the formula, it has to have +1. And the reason why is because, like you said, oxygen's -2. That we know for sure. It will never change. So in order for Cr2O to be an ionic bond, the positives and negatives have to cancel out. So the only way for this to work is if chromium is +1 and there's 2 of them. If it's +1 each, 2 of them makes +2, which cancels out with the oxygen -2 and makes it work out. Chromium 2, let's say it was chromium +2, for example. You'd have 2 of them, which would be chromium +4, right, at the end. So +4 chromiums doesn't equal -2 of an oxygen. That wouldn't work out. So you can have chromium 2 oxide. Or actually, you could have a lot of things. You could have this. This is, we'll go over that in a second. But does that make sense for this one? Chromium 2. This would be chromium 1 because each, so the thing is the transit, that's why I gave this example, is because the Roman numeral tells you the charge of each of the metals, not the charge of the metal total. I wanted to give you an example that has more than one ion, right? So you have iron here, iron and ion sound the same. But one of the first time I taught this class, I was saying the word ion, I-O-N, and one of the students thought I was saying iron. And so they started writing that because I didn't think that's something that someone thought. And I'm not saying they're dumb or anything. I'm just saying like that's a common misconception, maybe because of the way I say it. So iron, ion, that's a thing. But what was I saying? I don't know. But yeah, so the chromium, each metal ion, the charge of each metal ion is denoted by the Roman numeral. So each chromium in this case has to be +1 because they have to cancel out when totaled, they have to cancel out with a negative charge. So there's, and the good thing with this, there's never going to be any transition nonmetals. There's only transition metals. So for all these cases, what you're basically doing is looking at the nonmetal, what comes second, figuring out the charge. After you figure out the charge, then you look at the metal and you try to figure out, okay, what does the charge of this metal have to be in order for this to work out? And in order for the positives to equal the negatives. Okay, cool. I hope that makes sense. Let's do let's do 2 more examples. So let's do this one, the one I just wrote, CrO2. So what would that be? So let's look at
4 oxide.
Perfect. Chromium 4 oxide. And the reason is you look at what you know. Oxygen -2. There's 2 of them. -2 times 2 equals -4. That means the -4 has to be, well, to go backwards, you have to have +4 in the positive end to cancel out with it. There's only 1 chromium, therefore that chromium has to be +4. And also, Kaylee, to answer your question, so oxygen we know is -2 from the periodic table. There's 2 of them. -2 times 2 is -4. That's how we get -4. So then the +4 has to come from the cation. And there's only 1 chromium. If there was 2 chromiums or 3 chromiums, it'd be different. But since there's 1 chromium, that +4 has to be in that 1 chromium atom. So you have to have chromium 4 oxide. You could do another example with chromium and oxygen. Cr2. 3O2. Nope, can't do that. Cr2O3. That's what I meant. Okay, so in this case, what would you get?
Chromium 3 oxide.
Perfect. So oxygen again is -2. There's 3 of them times 3, -6. Chromium has to be +6. But there's not one of them. There's 2 of them. So this +6 needs to be divided by 2 or split into 2 different metals. Chromium 1 and chromium, or one of the chromiums and the other chromium. So if that's the case, each chromium would have to be +3. Since +3 times the 2 chromiums equals +6, which cancels out with the -6 for the oxygens. So this would be +6 at the end of the day, -6. Okay.
I have a question.
Yes.
So if it was Cr, if there was no 2, if it was just CrO3, would it be chromium 6?
Yeah, that's
yeah.
totally possible. Yeah, chromium 6. Chromium doesn't do that, but the process is right. Everything you said is correct. So you do, sometimes you have, some of these ions can actually be +6. But yeah, it would be, so to write your example down, CrO3, since 3 times -2 for the oxygen is -6. There's only one chromium. This chromium would have to be +6. You'd have chromium 6 oxide. Okay, let's do some more examples. We'll do a couple more. Erase this. All right. So let's do the one we forgot to do here. So CuO, what's that?
Copper 2 oxide.
Perfect. Copper 2 oxide, because we have our oxygen again, right? Oxygen's -2. Copper would then have to be +2, so it would be copper 2 oxide. So we'll do another one. We'll do different elements this time. Let me pick. Let's see. Okay, cool. Let's do. Nip. We'll do we gotta put the subscripts. Think about this for a second. All right, let's do these 3. So we have Ni3P2, Ni2O, and NiCl. That should be 4. NiCl4. Okay. So the first one, this Ni is nickel, by the way. So any thoughts? So phosphorus, I'll give you the answer for what charge it is based on where it is in the table. Phosphorus is in 5A with nitrogen. Therefore, the charge of it is -3. So who can give me the name?
Nickel 2 phosphide.
Perfect. Nickel 2 phosphide. And you don't have to write the Roman numerals in parentheses, but I tend to do that. So that's the conventional way of doing it. But regardless, yeah, nickel 2 phosphide. And the reason is because phosphorus is -3. There's 2 of them, so that means -6. So and then that means there needs to be +6 for the positives. You need to distribute that +6 into 3 nickels, since it's nickel, there's 3 Ni3, right? So each nickel has to be +2. Perfect. Another way to do it is, watch this. You're gonna hate me for this because it's a lot easier, but I wanted to teach you the method first. So you write it out, and then you do this. It's called the crisscross rule. You take the numbers from the opposite side and put them to the top, and that becomes a charge. So this becomes Ni2, and it would be 2 plus since it's a metal, and phosphorus would be not just 3, but -3. And then you'd see automatically, oh, it's nickel 2. So yeah, that's a shortcut. Mind blown. So that's called the crisscross rule. But I don't like teaching it because, well, it's good to know, but it's good to know after you know the math. Because it doesn't always work. You can't use it blindly. But it works for 99% of the time. If you had something like, if you had something like, we went over this one already, Cal, right? Calcium oxide. It wouldn't work for calcium oxide because if you write calcium oxide, you would think, oh, calcium is +2. Oxygen is -2. If you do the crisscross rule backwards, the formula would be Ca2O2. That's wrong. It's CaO. So it works most of the time, but the math is the most important. So know your positives and know your negatives. The idea here is that in every ionic bond, you're going to know something. You're going to know the nonmetal, at least. And from that nonmetal charge, you can deduce the metal's charge if you don't know it already. Okay, next one. Ni2O. Any guesses? Or any answers? Not nickel 2.
Nickel 1 oxide.
Good. Nickel 1. Good. Good job, Juan. Anyway, who said that? Who said it on the?
It is Devin.
Oh, Devin. Okay, I thought it was. All right. Good job. I just want to give credit where credit is due. Okay, so nickel 1 oxide, and the reason, oxygen -2. Therefore, the positives have to be +2. There's 2 nickels. Each one has to be +1. So nickel 1. All right, I think we beat this dead horse, or whatever you want to say. I hate that expression. I like horses. So that's disrespectful to horses. But we kind of beat this into the ground. So Kaylee, oxygen is always -2 because it's in group 6A. And so when it gains 2 electrons, 1, 2, it becomes -2. Okay, last one, NiCl4. Who wants to do that one?
Nickel 4 chloride.
Yes. I think you said nickel 4 chloride. And if you did, you're correct. Good job. So you have chlorine, we know is -1. It's in 7A. There's 4 of them, meaning -1 times 4 equals -4. To cancel out the -4, you need +4. So that's why nickel is 4. Good job. All right, cool. So hopefully you all understand how to do that. That's a good skill to have. So now with the things we went over, just to recap, you have normal ionic bond naming. Now this, even though we talked about Roman numerals for the last 10 minutes, this is only for transition metals, for metals that you don't know the charge of. Remember, if we go back to things like sodium chloride and magnesium oxide, you know the charge of both cation and anion. So there's no need for the Roman numerals, meaning by you know both of them. This means that based on the table alone, you can tell both of them based on their position. Okay, so now we're going to move forward. We're almost done, actually. Only like 12 more slides. Yeah. So the next thing we're going to cover is covalent bonds. So covalent bonds are different. They do not involve metals at all. So ionic bonds is a good thing to know. So I'll put IB. Ionic bonds is a metal plus a nonmetal. Covalent bonds, on the other hand, are all non-metallic. So nonmetals bonding together, and they form by the sharing of electrons rather than gaining or losing. So when two atoms share a pair of electrons, they tend to, or either one pair, two pair, or three pair at most, they tend to become covalently bonded. So here's a good example of that. On the bottom, you have two atoms, and this is what it means by sharing electrons. Instead of the electrons, since the electrons are always moving, they're going around the nucleus. But if they're a shared pair of electrons, they're going around both nuclei. And this makes them really strong together. So it makes a really strong bond. In general, covalent bonds are stronger than ionic bonds, but it varies. So like the strongest ionic bonds are weaker than weaker covalent bonds, and the strongest covalent bonds, like triple bond, is stronger than all of them. So there's different types. But let's talk about more of the theory of why this happens before we talk about naming. So I'll use this place to write. Now we know I really talked about that for a while, why ionic bonds form. You have the transfer of the electron induces a charge of positive and negative. The positives and negatives are then put together. So Kaylee, to answer your question, covalent bonds are just nonmetals. Ionic bonds have metal and nonmetal. So that's important to know. Okay. So when you have two, let's just do an example. Let's do oxygen, right? You have oxygen, and then you have another oxygen. Let's just talk about the outer shell. Well, I'll just put on the bottom, oxygen. Because I picked the wrong letter. I picked O. It looks like a nucleus. So we have two oxygens. And then each oxygen is going to have 6 valence electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And if you remember from lab, we talked about this thing called electron dot structure. Or did we? That was us, right? Yeah, I think so.
That was the last.
That was on Wednesday, right?
Yeah, Wednesday.
Okay, I'm not crazy. All right, cool. So we did this, and it probably didn't make any sense because we didn't get to this part yet. But those are all representations of covalent bonds. Now, for oxygen, remember the octet rule. A lot of remembering here, but remember the octet rule from like 20 minutes ago, 30 minutes ago, where the goal of these atoms is to get 8 electrons. Now, if you have a metal and a nonmetal, they could do that by making an ionic bond. But if you have 2 nonmetals, it's impossible to do that with ionic bonds. Because if you're like, oh, oxygen, I need 2 electrons. Let's like talk to be in perspective of personify the oxygen. Oxygen number 1 is like, I need 2 electrons to make 8, since I already have 6. Give me some. This oxygen's like, no way, man. I already have 6. I need 2 more also, just like you do. Too bad there's no sodiums or iron or any other metals around. What do we do? Oh, I have an idea. What if we share 2 electrons each? And he's like, damn, that's a pretty good idea. All right, let's do it. So what happens? Let's make a line between 2 electrons. If you share 2 electrons each, and they're considered, when they're shared, they're considered to be part of both atoms. Let's count them again. So for oxygen number 1, you have 1, 2, 3, 4, 5, 6, 7, 8. Good. And for this oxygen, it's exactly the same. You have 1, 2, 3, 4, 5, 6, 7, 8. Good. So this means that a covalent bond is nature's way of making two nonmetals bond together and be happy when there's no metals nearby, because they can't take electrons from somewhere. They have to share them. That's kind of neat how that works out. That's how smart the elements are.
I have a question.
Yes.
So it's basically like they're transferring it back and forth from each other over and over.
Yeah, that's a good way to think about it. They're transferring it back and forth so fast that you can just say it's sharing. These electrons are moving based on the GIF from before.
So yeah, it moves like an
Yeah.
infinity
Yeah,
sign.
exactly, exactly. They're moving so fast, like very, very quickly, that it's basically they're in both atoms at the same time almost. But yeah, that's the good way to think about it. You're right. Okay, so that's one example. Let's do another one. And it's not, and so this bond, since there was two electrons shared, that's called a double bond. So let's do one where it involves a single bond. Do hydrogen and chlorine. So chlorine only has, or not only, but has 7. And hydrogen only has 1. Now, hydrogen doesn't follow the octet rule. Doesn't want 8. Hydrogen's too small. We're clear to know what these are. I don't even write the name. So hydrogen is too small to have 8 electrons in it. So it's only going to have 1 electron. But then when it doesn't want 1, and it wants 1 more to get to 2. And it's based on its electron configuration. It can maximally hold 2. So for chlorine is like, oh, I have 7. I need 1 more. Hydrogen's like, oh, I need 1 more also. Too bad there's no sodiums around or any metals. What do we do? All right, we'll share 1. If they share 1, then they're both happy. Hydrogen has 2. Chlorine has 1, 2, 3, 4, 5, 6, 7, 8. Good. And this is called hydrochloric acid. So yeah, that's pretty cool, right?
Wait, I have a question.
Yeah, what's up?
The covalent bond itself is named hydrochloric acid, or
So no. So that's just this case. So there's covalently bound acids, but we're not going to learn about that today. We'll learn about the regular covalent bonds like we saw before. Well, really, the O2 was just oxygen gas, but something like CO2, that's carbon dioxide. So most of the covalent bonds are not acids. So we're going to learn about the normal naming scheme of them. When they become acids, it's a little bit different. So we're not really going to talk about that. That's a good question. So let's do CO2. That's a good relevant example. All right, so CO2 happens to bond like this. And carbon has 4 valence. 1, 2, 3, 4. And each oxygen has 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. So if you have a soup of all these atoms and they all need to be happy, there's only one way to do it. And they all need to have 8 electrons. So if oxygen's like, oh, I need 2 electrons, where are you? And this oxygen's like, oh, I need 2 electrons also. All right, let's do what we did before. Wait, then we're leaving carbon out of the mix. We don't want to exclude carbon because he's crazy. We need him to be chill also, right? Because carbon only has 4 electrons here. He's nowhere near happy. He needs 8. So if the oxygens can totally make a bond by themselves and make oxygen gas, which is very stable, like we saw before with a double bond. So that would look like this. And then you have the 1, 2, the lone pairs. But that would be leaving out carbon. So carbon, they have to be like, oh, fine, we'll include carbon. All right, carbon, what do you want? Oh, I need 4 electrons. The oxygen's like, all right, oxygen A, how about I give 2 electrons to you and you give me 2 electrons, so I'll be happy. Carbon's like, all right, I'll do that. But then after that, I still need 2 more. So let's do that first. It makes a double bond with one of the oxygens. Now this oxygen's happy because it goes 1, 2, 3, 4, 5, 6, 7, 8. Oxygen 1, oxygen A is happy. Carbon at this point, it has 1, 2, 3, 4, 5, 6. Closer, but still not happy. So this carbon's like, oh shit, I said shit. Well, whatever. I need 2 more electrons. And then oxygen B is coming along. Oh, so do I. Do you want to do the same kind of bond you did with oxygen A and do a double bond? Carbon's like, sure, that'll make both of us happy. It's all right. Let's do it. Done. Now oxygen B has 1, 2, 3, 4, 5, 6, 7, 8. Good. And now let's check on carbon. Carbon was very needy. It needed 4 electrons. So it has 1 bond, 2 bond, 3 bond, 4 bond. Each bond happens to have 2. So 4 times 2 is 8, and we're good. So carbon is satisfied. And they're all satisfied. And
I have
you can
another
try
question.
this all day. One second. You can try this all day and try to think of a different arrangement, but this is the only arrangement that CO2 will be happy. Yes, your question?
So if CO2, the reason there's 2 oxygens because carbon needs needs 4 bonds to be happy. How does carbon monoxide work if there's only 1 oxygen?
Good question. So carbon monoxide is not a stable molecule, which is why it's kind of deadly. Here's what happens. So carbon monoxide forms a triple bond. And carbon, you're right, needs 4 bonds, but it has a lone pair of electrons in the carbon. That's not good. That's what makes it a little bit unstable. So, and it's very reactive. So carbon, this is what makes it deadly. So this carbon in carbon dioxide wants to partake in 1 more bond, right? Because it needs 4. So in order to do that, when you inhale it, it will get into your bloodstream. And once it does, it will bind to hemoglobin. And what it will do is it actually competes it doesn't compete with CO2, it competes with oxygen itself, O2. And since CO, carbon monoxide, is more reactive than O2, since O2 is happy, it will bind to your hemoglobin where the oxygen is supposed to bind. So hemoglobin has iron in it. It's basically a protein that transports oxygen from your lungs to your bloodstream to your body to survive, and to your brain and everything. So it transports your oxygen around your body. Once carbon monoxide gets in the mix, carbon monoxide is so strong and so radical and so reactive that it will bind in the spaces where oxygen on hemoglobin is supposed to bind, thus kicking out oxygen. So oxygen can no longer bind to hemoglobin, meaning you are not taking oxygen to the correct places in your body anymore. Instead, you're taking carbon monoxide. So carbon monoxide poisoning is really the lack of oxygen. There's nothing intrinsic about carbon monoxide that makes it deadly. In the only thing it does is it blocks oxygen from getting to your bloodstream because it's more reactive than oxygen. So that's a very good question you brought up. And who was that?
It was me.
Oh,
Ash.
Okay, Ash. Yes. Good job, Ash. But yeah, so that's a little lesson about why you should stay away from tailpipes. Yeah, because they have carbon monoxide. And why the carbon monoxide alarms in your houses or apartments are very important, because you can't smell it either. So, and you can't hear it. So you just have to, or you can't taste it either. So the only way to detect it is by a detector. Okay. And a good thought is like, why hasn't evolution overcome this already? And the answer is because there's not much carbon monoxide in the atmosphere. There's no need for us to have an evolutionary mechanism to kick out carbon monoxide from hemoglobin, because the percentage of people, let's say before industrial times, no one died of carbon monoxide poisoning before like modern civilization, because there's no carbon monoxide. Maybe a little bit would be produced from like different like like natural gas chambers and like different swamps and stuff, but nothing that's significant. Like nobody had rooms that had pipes burst and with carbon monoxide coming out like we do now. So there was no need for it evolutionarily. So, but yeah, that's a silent killer. Okay, so let's talk about naming the covalent bonds. And it's actually a bit easier than the ionic bonds. So when you name them, you say the first name of the element. And then you are going to add a prefix. So covalent bonds now are using prefixes. Ionic bonds, we never used magnesium dichloride or any of that stuff. Never. We never used them because of the math that I explained before. But now that we have covalent bonds, there are multiple combinations that are acceptable of bonds with the same elements. And we just went over two of those being carbon monoxide and carbon dioxide. If you just write carbon oxide, that's not telling the reader which one of these it is. So we have to have prefixes to tell the reader the reasons, tell the reader what it is. So what we're going to do first is the prefix and then the name of the first element. But if the first element only has one atom, you do not use mono prefix. That's only for the first one. Why is that rule a thing? I'm not sure, but it's the rule. So we're not saying this is not monocarbon dioxide. It's just carbon dioxide. Same for carbon monoxide. It's not monocarbon monoxide. And that's because when the first element only has one atom, you're dropping the mono. You're dropping the prefix. So every other prefix is relevant. So if you had C2O, it would be dicarbon monoxide. And we'll do examples. The second name, the second element, is always the prefix, just always the prefix, even if it's 1, if it's 2, if it's 20, whatever. The root name, and then you're staying with this IDE ending. The IDE ending stays the same as it did for ionic. So this would be dicarbon monoxide. Let's do some other ones. This would be dinitrogen monoxide. This would be dinitrogen dioxide. This would be trinitrogen dioxide, etc. So you kind of get the point. Now it's a bit easier to name. And now let's look at prefixes. So the prefixes 1 through 4 are the only ones that are kind of new to you, or they might be new. They make sense, but they're kind of new. So mono means 1, like mono y mono, 1-on-1. Di means 2, like dihedral angle, I guess. I don't know. I'm about to say dicycle, but that's bicycle. It's not bi, it's di. Tri means like tricycle, like 3. Tetra means 4, like Tetris or tetrahedral. In Tetris, you have each block is composed of 4 little blocks. And everything after tetra is just the shapes, like pentagon, hexagon, heptagon. So you should be familiar with those. But the first 4, maybe you want to take a look at. So let's do some examples. Oh, their answers are there for you. Okay, cool. We'll do a couple more. But yeah, so SBr4. So there's 1 of the first element, so you write sulfur, and there's 4 of the second one, you write tetrabromide. P2O3, diphosphorus trioxide. So you're just writing as many as there are. It's kind of straightforward, not really much to explain there. Let's do some more. Let's do oh, that's not it. Should I have another one? Okay, let's do a couple. So OF2, what is that?
Oxygen difluoride.
Perfect. Oxygen difluoride. What about SF6?
Sulfur hexafluoride.
Perfect. Sulfur hexafluoride. And I'll change this one. What about this one now? P2Cl5.
Diphosphorus pentachloride.
Wow, perfect. Phosphorus pentachloride. Nice job. Awesome. Good. So that's how you do covalence, really. So Kaylee, I'll do it. I guess I'll do one more. I just gave 3, but I'll do another one. Let me think. Think. Yeah, what about this one?
Dicarbon tetrachloride.
Perfect. Dicarbon, since you have more than one carbon, needs to be the prefix. Dicarbon tetrachloride. Awesome. Good. All right, so let's move on. The last thing we're going to cover is this concept of electronegativity. Now, this kind of relates to, well, not kind of, this relates to covalent bonds. So we know that covalent bonds are the sharing of electrons. So I'll draw another picture of that. So let's say you have 2 electrons that we'll just say are in the middle, and there's like a rope, and then you have, I don't know, chlorine, and you have hydrogen, right? So these electrons are in the middle. But electronegativity, we didn't talk about that yet. That means it's the measure of the atom's attraction for electrons in a bond. So based on these numbers, we don't have to memorize these numbers at all. You can tell which element likes to have electrons more in a covalent bond. And the answer is fluorine. Really, fluorine is the highest. But the way the trend works is it increases going from, that's a bad diagonal line. That's terrible. So it increases going from the bottom left to the top right. Like this. Like, I'll try better line. It's better. So on the bottom left of the periodic table is the lowest electronegativity, meaning they don't want electrons and they don't care, which makes sense because we learned that all these metals in general, they want to lose the electrons. So even when they're in a bond, they don't want to keep them. And then the nonmetals tend to like electrons a lot. So they like to take them. And fluorine is the most electronegative atom. And it makes sense based on the word electronegative, meaning electron, I don't know. It has to do with liking electrons. So it's a property. Now what this means in a covalent bond is that the picture I just drew of H and Cl with the electrons in the middle is not how it works at all. Since chlorine and hydrogen have a very different electron affinity, or sorry, that too, but electronegativity, hydrogen is only up here, hydrogen's to the left, which means it has a very low electron affinity, only 2.1, and chlorine is higher, it's towards the right, and has a 3 electron affinity. This means that the atoms with the most electronegativity will pull the electrons more towards itself because it likes them more. So in reality, this covalent bond looks like this. All the electrons in the covalent bond are very close to chlorine. Even though the bond is still occurring, it's just like a tug of war where you clearly have somebody that's stronger. It's more pulled towards the stronger person. And stronger for electrons means electronegativity. So the ones with the most electronegativity are going to be pulling that rope a lot harder, and the electrons are going to be closer to it. Okay. So what this means, so does that make sense, first of all, that concept of electronegativity? And the only thing I would expect from you on a test is if I give you an example using this trend that on the periodic table, that let's say if I give you silicon and fluorine and I ask you to tell me if it's polar. We'll talk about polar in the next slide. And oh, their difference in electronegativity is big, so they're going to be polar, right? So, and even if you don't need to know the numbers by that, you just need to know the trend that it's going to go from bottom left to top right of increasing electronegativity. So this idea that the electrons are unequally shared, what this does is it actually gives the covalent bond, the entire bond, partial charges. And what partial charges are just, I don't know, charges that are partially on one side and partially on the other. So if chlorine has the electrons pulled towards it, it's going to have a partial negative charge because it has more electrons near it. If you have hydrogen that doesn't have any electrons near it, it's going to be partially positive charged. This is what creates a polar bond. So that brings us into our next idea. And here's HCl. So HCl is called polar. And polar means that it likes water, that because water is polar. And it has, more specifically, it has this difference in electronegativity between atoms in its covalent bond. So since chlorine has higher electronegativity, it will pull the electrons closer to its center, thus giving the chlorine a minus charge, a partially negative charge, and the hydrogen will have a partially positive charge. That's what this delta, this is a lowercase delta, and that means partial charge. That's the sign they use. So yeah, that's that. And you can determine a bond's polarity by the element's position on the periodic table. If they're very close to each other, such as phosphorus and sulfur, they won't have much of a polarity. It won't be that polar. It still will be. They're different, but not that much. If you have, let's say, fluorine and something like that's far away, like fluorine and boron, they're going to be very polar. So because they're a bit further away from each other, meaning their capacity to pull an electron is going to be way different. Fluorine's a strong man here. Fluorine can outpull any element when it comes to electrons, even oxygen. Oxygen's number 2, but fluorine still wins. Okay, so you can have bond polarity. That's what I talked about already. And we're not going to focus on the numbers. So don't worry about that. Just worry about the trend. Now, if I give you, I'll just give you another one. If I give you, here's a trick one. Well, before that, if you want to break it down into the different types of bonds we learned today, there wasn't just ionic and covalent. There was ionic, obviously, which is the metal plus nonmetal. Then there's polar and nonpolar covalent, which are just different types of covalent. We learned covalent. We learned how to name all of them. But for polar, that means it's a covalent that has a significantly a large difference. So larger, I'll put EN, electronegativity difference. So different, the signature, the symbol for difference is this capital delta. So larger difference in electronegativity, and nonpolar is a small difference in electronegativity. Now, again, you don't need to know the numbers. So for something that's nonpolar, I'll give you like F2. So F2 is not polar. Even though fluorine has the highest electronegativity, there's 2 fluorines. So if you have 2 strong men that are equally strong pulling the rope, what's going to happen? It's going to stay in the middle. So then nothing's going to move. The electrons are going to be in the middle, and it's going to be nonpolar. So for polar, they are going to have a bigger difference, and that you could tell that based on their position on the table. So yeah, so I think that's all I'm going to say about that. Okay, so the actual last thing is, I don't know why this wasn't included in Ionic. I should move these slides, but there is. All right, so is there any questions on that, first of all, before we move on? We're almost done. No? Okay. If you think of questions later, you can either rewatch the video or let me know. Email me, and then my office hours are on Thursday also. Not many of you visit me. That makes me sad, but you feel free to bother me. Okay, so let's combine everything we learned so far. And it gets a little bit, this isn't complicated. It's just the way trust me, it won't be that bad. Now, there's this thing called polyatomic ions, which, imagine if you had a covalently bonded complex, right, of more than two atoms, two or more atoms that are just covalently bonded together. But that covalently bonded complex itself has a charge. And you can see those examples here. Hydrogen carbonate, it's HCO3. They are all covalently bonded together, right? There's no metals here. Same thing with a lot of these, there's no metals. Most of them, there aren't any metals. Some of them do. Chromate has metal. But like acetate doesn't. Most of them don't. So this covalently bonded group, the entire group has a charge. So that means the entire group can interact with a positively charged ion, because you see most of them are negative. The only positive one is ammonium. So these polyatomic ions, what they mean is a group of covalently bonded atoms with a charge, and they have specific names. These polyatomics can partake as the anion, or for ammonium's case, the cation, in ionic bonds, whereas a normal metal could be the cation. So there's a bunch of names here. This is some of them, not all of them. And to cut to what you're thinking of is, oh my God, do I have to memorize these? The answer is no. So you do not need to memorize these. I will give them to you when you need them. So the question will ask, what is the name of NaCN? And I will give you on the bottom, Cn minus 1 is cyanide. So the answer is, oh, sodium cyanide. So you view the entire thing, the Cn, as its own group. So this would be sodium cyanide. So that brings me into naming with these. When you go into naming, it's super easy. You don't have to modify anything. You just write the name of it. So unlike with the anions, you have to write, oh, I got to change the IDE, I got to change the ending, whatever. You don't have to do that here. With the polyatomic ions, you just write the name of them. So calcium nitrate, CaNO3 The same rules apply as normal ionic bonds, where the charges of the positives need to cancel out with the charges of the negatives. But the charges of the negatives in these cases are going to be the polyatomics. They're going to be more than one atom in there. And so NO3 is a -1 charge. Two of them need to cancel out a calcium. So it would be calcium nitrate, like that. So yeah, then you can combine everything we learned today into something like this. Let's figure out FeNO3 3. Let's do this one. So NO3 is nitrate. It's right here. It has a -1 charge. So what would be the name of this?
Iron 3 nitrate.
Perfect. Great job. Iron 3 nitrate. So you just say the name of the polyatomic, and then everything else, the rules apply the same. Where iron is a transition metal, you have to figure out the charge. NO3 is -1. There's 3 of them. This has to equal -3. And then Therefore, the iron has to be +3. Cool. Good. All right. Here's some other examples. Here's the only type. So this is the only time. This is a trick thing. If anyone asks you, and maybe in Chem 2 or something, I might ask you, what is the only ionic bond, or one of the only ionic things, or name an ionic compound that doesn't have any metals in it? That's weird because the definition of it is a bonding of a metal and a nonmetal. So the answer is anything having to do with ammonium, right? So this ammonium up here, if you look at the previous slide, has a +1 charge. It's one of the only cations that happens to be a polyatomic ion. So it's the only, and hydronium is another one, but you don't really see hydronium in ionic compounds. You see mostly ammonium. So something like ammonium sulfate, where SO4 is sulfate, this would have no metals in it, but it would still be considered ionic. So that's weird, but that's just a little nuance. Okay, so that's basically it. Now, what I do have here, I have some videos. So if you need help more on ionic and covalent bonding, that's good. And it's right there, a YouTube video. Naming ionic and covalence is right there. And in Crash Chem, there's some good videos on ionic and covalent and also naming. Now, here's a summary slide of all the naming. So those of you who are Fairly Odd Parents fans out there, used to watch that when you were little. I did too. And here are the rules, right? So in ionic bonds, this kind of summarizes everything. For ionic bonds, it's between mostly metals that are positively charged and nonmetals that are minus. The metals lose the electrons while the nonmetals gain them. The metal cation total charge should be equal and opposite of the nonmetal anion total charge. And here are some charges you should know. 1A is +1, 2A is +2, 3A, just aluminum, is +3, 7A is -1, 6A -2, 5A -3. The transition metals have a variable charge. They don't follow these rules. You don't know. It depends what they're bonded with. Naming with transition metals uses the Roman numeral, like we talked about. Polyatomic ions are simply another element with its own charge. You consider them like that. So it's just a group, and you put that group together. And they use the IDE ending, or sorry, you normally use the IDE ending except when you're dealing with polyatomics. So, and then covalent, you can see how ionic is very long. Covalent, the list is not that long. It's an easier naming process. It took us like 3 slides to know it. So covalent, it's between 2 nonmetals or more. It doesn't really talk about charges, but there are partial charges when we're talking about polarity. The first element, you write the name of it. If there's more than one, you use the prefix. For the second element, you write the name of it with the IDE ending, and you always write the prefix, no matter how many there are. So that summarizes chapter 4 for you. So I'm going to stop the recording.